December 1944, Ardennes, Belgium. General Alfred Jodl, Chief of Operations of the German General Staff, was confident that the surprise counterattack on the Western Front would break the backbone of the Allies. His maps indicated frozen terrain, reduced visibility, dominance of the surprise factor, the prediction, quick victory. But what he didn't know, and what his soldiers would learn the hard way, was that in the silence above the forest, a new weapon had been deployed. This gun made no noise when it arrived. It did not depend on luck, vision, or trajectory calculation, she thought. And when he thought, he exploded, not on the ground, but in the air, exactly where the enemy was. It was the beginning of the era of smart munitions, and no German was prepared for it. What seemed like just another shell in the American arsenal was actually the most secret project after the atomic bomb. An apple-sized capsule capable of detecting its target by radar and exploding with mathematical precision, produced by the millions, invisible, unstoppable. This documentary will reveal why the radar proximity fuse not only worked, but redefined the concept of military power in the 20th century. It was the end of an era. But before we dive behind the scenes of this weapon, there is a statistic that defines the brutal impact it has caused, and that few know about. In less than 2 years, proximity fuses were responsible for shooting down 25,000 enemy aircraft, destroying 5,000 flying bombs, and eliminating more than 10,000 German soldiers in just 2 weeks in the Ardennes. No other invention, with the exception of radar and the atomic bomb, has caused such damage with such frequency, precision, and silence. The irony: in 1944, Luftwaffe technicians even examined an intact specimen. They declared it impossible, and they laughed. They laughed until the next salvo fell from the sky and exploded before touching them. If you value history, technology, and the forgotten details that changed the course of the century, consider leaving your support. This helps us to continue to reveal the invisible weapons that have decided the fate of the world. Even before the first bullet was fired in World War II, the US High Command knew that there was a war that was already being lost, and it wasn't on the battlefield. It was in the tables, in the charts, in numbers. Since 1918, conventional artillery doctrine has faced an insoluble dilemma: how to hit a moving target miles away from the ground. In World War I, it took more than 8,000 rounds to shoot down a single plane. 2 decades later, even with radar and better guns, the average efficiency had improved little. Air warfare, which became the new axis of the conflict, required a response that traditional artillery could not give. Each projectile fired was a gamble, and most missed. Anti-aircraft defense was, in practice, a roulette wheel with explosives. To shoot down a bomber, the Allies needed more than 5 tons of ammunition. The Germans knew this, and they were counting on it. In his calculations, the Americans would never be able to build a reliable shield against the sky. And in part, they were right. The radars indicated the position. The cannons fired. But the connection between these 2 points was still analog, slow, and desperately inaccurate. It was this gap between detection and impact that gave rise to the most audacious idea of the conflict. What if the ammunition thought for itself? What if, instead of programming the location of the explosion, it simply detected the target and exploded at the exact moment, inches from it? The concept sounded like science fiction. A miniaturized radar, capable of resisting 20,000 times the force of gravity in the shot, working with its own energy, calculating distance in microseconds, and all this inside a cylinder the size of a lamp. But the urgency left no room for skepticism. In 1940, while Hitler was advancing through Europe with blitzkriegs and tactical bombings, the American army was still using doctrines from 1918. It was the greatest industrial power on the planet, with the most advanced production system in history, but technically blind to the sky. President Roosevelt had been clear. The next war would be decided by the ability to respond quickly and by the ability to think differently. German engineers, on the other hand, relied on mastery of the surprise factor. The Luftwaffe didn't have to be invincible, just superior long enough. And for this, they relied on the doctrinal inertia of the Allies. Nazi calculations were cold, an average of 5,000 rounds for a single hit. Allied ammunition depots would not hold out for long. Germany, even with fewer resources, believed that its advantage lay in efficiency, in the quality of engineering, of discipline, of science applied to combat. The fatal mistake was to ignore what Americans knew how to do better than any other people in that century: multiply ideas on an industrial scale. A statistic ignored by the Germans, but documented in the Washington archives, shows this accurately. In 1943, while Germany produced about 200 pieces of anti-aircraft artillery per month, the United States manufactured 6,000 guns, with 3 times the ammunition. If this surprised you, comment now. Logistics wins, but quantity was not enough. What the Americans sought was to break the logic of the lottery. The cannons needed to stop shooting blindly. It was necessary to reverse the game, that the ammunition itself would find the enemy, and for that, mathematics was the new battlefield. The time between detecting an airplane and calculating the correct distance to detonate a shell was less than 2 seconds. And in those 2 seconds, everything could change. If the altitude, speed, or angle changed, the shot missed. As much as radars and operators did their job accurately, artillery remained a dumb mechanism. American scientists began to call this the broken chain of death. Detecting was easy, calculating was possible, getting it right, it was rare. The solution: take the calculation out of human hands. The concept of the radar proximity fuse arose in this precision vacuum. An autonomous unit, which emitted radio pulses, calculated the return time, recognized proximity, and fired its own detonation at the exact point of maximum lethality. It was the first time that a weapon did not wait for orders. It made decisions. In theory, it seemed impractical. In testing, it looked promising. But in war, it was all or nothing. And this nothingness was what the Germans were not prepared to face. An internal Wehrmacht document, intercepted months later, revealed blind reliance on tactical air dominance. The Americans lack immediate reaction and surgical precision. Our advantage is assured in the heavens. This sentence, written in 1942, would be reread with astonishment by the German officers themselves 2 years later. In trenches, field hospitals, and post-battle records, always accompanied by the same comment: they learned too quickly. The collapse of that trust began quietly in anonymous workshops across the United States. But the first real proving ground would soon come, and with it, a new generation of smart weapons, still invisible, still underestimated, but increasingly lethal. The enemy expected resistance. What he would find was something he did not understand: an ammunition that calculated, decided, and exploded on its own. In September 1940, as London burned under the roar of German bombs, a silent group of British scientists and officers crossed the Atlantic with a briefcase that contained no target maps, but the future of warfare. It was the Tizard mission, named after Henry Tizard, a physicist and military advisor, that carried among its priorities the most daring of the projects not yet accomplished: an ammunition that would detect by itself the moment to kill. At the height of the Battle of Britain, with the RAF holding out on the edge and the morale of the British population teetering between bravery and collapse, the War Cabinet made a historic decision. They would hand over to the United States their greatest technological secrets: the cavity magnetron, the basis for modern radar, the acoustic depth pump, photoelectric effect detonators, and among them the rudimentary concept of a radar proximity fuse. It was not a finished technology. It was an idea, a technical sketch, promising but still impossible to be manufactured on a scale under the daily bombardments that London suffered. It was, in Tizard's words, the price of survival. Aimed, and unlike the Axis powers, which centralized power in ideologies and men, the British bet on collaboration with an industrial partner capable of accomplishing what they only envisioned. The American reception was, at first, ambivalent. The U.S. Army, still stuck to conventional doctrines, hesitated in the face of the proposal, but among civilian scientists, the impact was immediate. When physicists at the National Defense Research Committee examined the fuse concept, a mixed reaction of fascination and urgency gripped the labs. It was an idea that challenged the limits of practical physics, a miniaturized radar encapsulated in an aluminum cylinder with the ability to emit radio signals, detect the return time, and determine, in less than 1,000th of a second, the distance to the target. And not only that, it had to survive the shot, operate autonomously, resist humidity, heat, vibration, and impact. Electronic technology at the time was fragile, expensive, and unstable. But the British had proven that it was theoretically possible. It lacked something that the United States had in excess: scale, resources, industry, time. It was then that, in a gesture of strategic pragmatism, the Americans decided to turn the improbable into the inevitable. Instead of trying to validate each scientific step before authorizing production, as the British did, the US applied its greatest asset. It relied on the power of mass-applied engineering. Under the leadership of the Johns Hopkins University Applied Physics Laboratory, and with direct coordination from the Office of Scientific Research and Development, the project was initiated in absolute secrecy. No competition between departments, no military bureaucracy, no committees. Resources flowed straight from Washington to the test benches. The orders were clear. No idea would be considered absurd until it was proven in the laboratory that it really was. While the Germans concentrated their efforts on weapons of terror, V-2 rockets, flying bombs, colossal tanks, the United States and the United Kingdom invested in invisible intelligence. The difference between the powers was in the paradigm. While the Third Reich sought superiority through fear, the Allies sought advantage through science. The Nazis laughed at the idea of a thinking capsule. The Americans prototyped it. The United States' choice to take over full fuse development marked a historic turning point. By importing the British idea and applying to it the Fordist logic of industrial multiplication, the Americans transformed a niche theory into armament on a global scale. And they did it in record time. Less than 18 months after the arrival of the British, the first working model of the VT fuse was ready for real tests, a feat unthinkable in Nazi Germany, where every advance was subjected to political scrutiny and favoritism by party officials. American confidence came not only from patriotism, but from mathematics. Internal technical reports showed that if the device worked, it would reduce anti-aircraft ammunition waste by up to 90%. A 90mm gun would go on to shoot down aircraft with 3 rounds instead of 30. Logistical calculations indicated that the massive use of fuses could balance air power with half the production effort. It was the solution that united what Roosevelt wanted most: effectiveness, secrecy, and moral effect. The decision was made. The project would gain top priority status, next only to the Manhattan Project. Germany, in the same period, was betting its resources on increasingly complex and centralized projects. The V-Weapons Division drained funds from critical sectors, and technical decisions were made by military personnel who believed more in symbolism than in feasibility. While American engineers welded mini-radars to assembly mats in Ohio, German engineers calculated the ideal orbit of a ballistic bomb that would only be dropped once. The contrast between the two mentalities is clear. On the one hand, the excess of complexity. On the other, the obsession with multiplication. And in war, Winning is not just creating, it's repeating. In December 1942, the first experimental batch of fuses was completed. About 100 units, made by hand, have undergone tests in extreme conditions. The failure rate was less than 3%. By the standards of the time, it was a technical miracle. The following month, the first examples would be sent to the Pacific for what would be the first real use of the new weapon. But what no one yet knew was that at the same time as the Americans were preparing this secret weaponry, the Germans would serendipitously capture an almost intact example of a projectile equipped with the new system. The technical report, written by Luftwaffe engineers, which will be revealed in the next part, contains the sentence that sums up all the arrogance that precedes the crash. This device is inconceivable in practical operation. They were right, and at the same time, completely wrong. Merle Anthony Tuve was neither a military man nor a politician. He did not carry weapons, nor did he speak on podiums. He was a calm physicist, with a low voice and discreet steps, trained in Minnesota, passionate about applied science and the idea that knowledge was only worth it if placed at the service of humanity. When he was called in 1940 to lead the development of a first-of-its-kind technology, a device capable of thinking inside a metal capsule, his response was immediate. Yes, not out of patriotism or personal glory, but because he understood with almost painful precision the human cost of every second lost. Tuve was a laboratory man, not a trench man. But he knew from the beginning that his role, although invisible, would be decisive. He understood that, in modern warfare, the silence of scientists would be more powerful than the noise of generals. At the helm of the Johns Hopkins University Applied Physics Laboratory, Tuve assembled an unlikely team: civil engineers, young theoretical physicists, radio technicians, watchmakers, and metallurgists. Few with military experience, but all with a common obsession: precision. The mission seemed absurd. To design a miniaturized radar that could fit inside a warhead, survive more than 20,000 times the force of gravity in the firing, operate with full autonomy, calculate distances in microseconds, and decide on its own the moment to detonate. Nothing like it had been done before. There were no ready-made formulas, no reliable prototypes. The project was so unprecedented that many didn't even know what they were trying to name, what they were trying to build. They called it a fuse, but they knew that it was, in practice, a rudimentary electronic brain housed inside a bomb. The culture of the laboratory reflected the urgency of the moment. There was no time for hierarchies. There was no room for vanities. The phrase repeated in the corridors by Tuve was clear: don't save money, save time. While the Germans centralized their research in departments headed by officers, the Americans relied on the creative chaos of their scientists. Every idea, no matter how unusual, was tested. If it failed, it was learned. If it worked, it was replicated. The prototypes were subjected to extreme tests: shocks, vibrations, temperature variations, magnetic fields. A working model could be destroyed in seconds to verify its robustness. There was no room for attachment. I just moved forward. Science there was not contemplative. She was aggressive. Each day of delay cost lives. Each advance, no matter how small, could save hundreds. Merle Tuve instituted something that the Germans never understood: a morally based chain of scientific production. No scientist there considered himself a weapons creator. Everyone saw themselves as builders of shortcuts to the end of the war. They didn't want to kill anymore. They wanted to kill less and more accurately. The concept was simple but devastating. An aerial explosion, carried out a few meters from the target, generates 3 times the lethality of a detonation on the ground. With this, it would be possible to shoot less, hit more, and, paradoxically, cause less collateral destruction. The engineers welding the first valves knew the numbers. An artillery salvo with clever fuses could stop an entire squadron of bombers before they crossed the horizon. It was a change not only in effectiveness, but in doctrine. The miniaturization of electronic components was the biggest challenge. In 1941, an ordinary valve measured 15 centimeters. Tuve required that the entire fuse radar be no more than 2.5 centimeters high, including antenna, oscillator circuit, pulse generator, and receiver. To do so, he turned to private companies that had never worked in defense, manufacturers of home radios, flashlights, even electric toy companies. One of them, Raytheon, created a special valve that could operate under extreme impacts without breaking the filament. Another, Crosley, developed a system of coiled antennas that took up a third of the previous space. Before long, Tuve's assembly line was no longer just an experiment and became a real production model, and with that, the weapon was no longer just possible. It became inevitable. Meanwhile, the Germans confidently watched the Allies' delay in reacting to the Luftwaffe's advances. Its engineers still sought superiority through range, designing intercontinental rockets and high-impact bombs. The idea of giving autonomy to a warhead was considered technically unfeasible. In 1943, the Luftwaffe published an internal opinion on the possibility of using electronic sensors for proximity detonation. The conclusion was categorical: highly sensitive to failures, impractical under combat stress, immune to miniaturization. Ironically, that same month, the Americans completed the 1,000th functional prototype. Tuve, however, refused any celebration. Each technical advance was followed by a new requirement: more stability, lower energy consumption, less weight, greater thermal tolerance. He knew that a single failure in the real field could jeopardize the entire project. And he also knew that the secret was as valuable as the technology. No engineer had access to the entire project. Each team worked in segments, often without knowing exactly how their piece would be used. The tests were conducted under armed surveillance, and the reports destroyed daily. What was at stake was not just a weapon. It was the balance of war. By mid-1943, with bench tests passed and final models approved, the first batches were produced in secret. 500 units, numbered, tracked and sealed. Merle Tuve personally signed the order. They would be sent to the Pacific and tested in real combat. The crew of the USS Helena, a Navy cruiser, would be tasked with firing the first near-fused projectiles at Japanese planes. The world didn't know it yet. Neither did the Germans, neither did the Japanese, nor the gunners themselves who would pull the trigger. But there, on that deck, the first smart weapon in history was about to think for the first time. When the first real tests of the proximity fuse confirmed the impossible, that an apple-sized capsule could think on its own and bring down planes before they crossed the horizon. The challenge ceased to be technical. It became industrial. And it was at this point that the United States demonstrated its most powerful weapon, the ability to turn an idea into mass production with a speed that no dictatorship could keep up with. The project left Merle Tuve's laboratory and was handed over to a secret consortium of civilian companies, most of them until then dedicated to the production of household items. A radio factory in New Jersey, a flashlight company in Pennsylvania, a hearing aid manufacturer in Chicago, and even a Christmas light assembly line in Ohio, all were converted into critical production sites for the new weaponry. The irony of this story is that the salvation of thousands of soldiers in the Pacific began at the hands of workers who months before packed garlands and strings of colored lamps. If you're enjoying unraveling these facts, show your support. Like and subscribe so we can bring you more in-depth content. The specs were absurd. Each fuse had to contain 6 miniaturized electronics, sealed against moisture, immune to vibration, and capable of operating under shocks of up to 20,000 Gs. Accuracy wasn't just desired, it was vital. A millimeter off the curve could compromise the logical sequence of firing and failure in the air. For this reason, the welding and assembly work was entrusted, for the most part, to women. About 80,000 of them, trained in record time, started working in 3 shifts, 7 days a week, in warehouses where each workstation was isolated by curtains and armed surveillance. Nobody knew what they were putting together. The orders came in sealed packages with fragmented instructions. Each worker dealt with a single segment. Only the supervisors knew the nature of the final product, and even they couldn't discuss the project among themselves. The secrecy was absolute. The result is unquestionable. Production grew like an avalanche. From 100,000 units a week in 1943, the numbers jumped to 20,000 a day in 1944, and exceeded 70,000 a day by the end of that year. No Axis country, with its centralized industries and vulnerable to bombing, could dream of something close to this scale. Germany, already in a collapse of resources, divided its production between tanks, rockets, and planes. The United States, on the contrary, standardized, replicated, simplified. Each component of the fuse was designed to be easy to assemble, difficult to disassemble, and impossible to spy on. Even the painting of the capsule was thought out, opaque, anti-corrosive, and without inscriptions, so that even if captured, the enemy could not decipher its function. Unlike Nazi propaganda, which celebrated each new weaponry as a mystical creation of enlightened engineers, Americans relied on the discipline of impersonal production. No name was associated with success. No face made the headlines. The design of the fuse was larger than any of its creators. It was a collective machine, a triumph of the sum. While the Germans invested in weapons that required individual heroes, the Americans built a system that dispensed with heroes, because it operated with such efficiency that victory became statistical, not symbolic. The real strength was in multiplication, and this multiplication was not limited to numbers. It was reflected in time. Each fuse produced took less than 2 hours from the start to the end of the assembly line. Each batch was tested in pressure and vibration chambers, simulating the real shots. Those that failed were immediately incinerated. Those who passed by went on to naval artillery lines, anti-aircraft batteries, and field shells. The logistical system created to store, transport, and track the fuses was as complex as the weapon itself. Each box had a physical tracking code. Every move was recorded. The troops who received them in the field did not even know what they contained. Just one order: arm carefully, high priority. The magnitude of the operation, however, remained invisible to the public eye. Not even President Roosevelt received a detailed report of the project in his lifetime. The security was such that the name Proximity Fuse itself was not used in the documents. They just called it VT Fuse, an acronym without explanation, created to confuse any attempt at espionage. None of the 80,000 workers knew the real impact of their work. It wasn't until years later that some discovered that the pieces they welded had saved entire ships from kamikaze attacks. That his fingers, steady before the microscope, had been the last line between life and death for sailors thousands of miles away. Meanwhile, the Germans were still trying to understand what was happening. Reports from the front began to mention a new form of explosion in American shells, one that occurred before impact, with frightening precision. The Luftwaffe was suspicious of more refined time fuses. Artillery officers believed it was luck or new shooting doctrine. No one even thought that the shells themselves were seeing the target. This conceptual blindness, more than a lack of resources, was what sealed the fate of German air superiority. In just 4 months, Allied airstrikes began operating with a new type of invisible shield. What used to require full salutes, now one shot was enough, and the enemy fell. In April 1944, a phrase appeared in a secret report by the Abwehr, the German intelligence service, intercepting Allied communications. The message read, "Top priority, recover intact American shell. Suspicion of embedded electronic device." It was late. They had finally understood, but the weapon was already in full use, and soon it would be taken to where the heavens were not the problem, but the ground. Because there, on the frozen front of Belgium, the VT Fuse would descend from the clouds to become the nightmare of the German trenches. January 6, 1943, Solomon Islands Sea. Aboard the light cruiser USS Helena, tension was constant. From dawn, signals from enemy planes were picked up by radars, and with clear skies, the crew knew that the Japanese would come in waves. The Helena, a veteran of Guadalcanal, had faced dozens of airstrikes, and her gunners knew exactly what to expect. Screams from the loudspeakers, running on firing platforms, the tense dance of Zeros cutting through the sky, and the hope that, among hundreds of shots, one would find its target. But that day, something was different. Among the shells loaded into the chambers of the 5-inch Bofors guns, some were marked with a discreet green stripe. None of the crew members knew what it meant. Just one order: use them only when authorized. When the first group of Japanese dive bombers appeared on the horizon, the order came over the radio: green strip, fire. The projectile departed with a metallic whistle, like any other. But when it reached 60 feet above sea level, something unprecedented happened. Without touching anything, he exploded, and out of the flash came the impossible: a Japanese plane plummeting in flames, without even being hit directly. The radar operators confirmed: air impact without physical contact. The crew was silent. There was no time detonation. There was no altitude calculation. The shell had thought to itself, and he had acted. It was the first time in the history of warfare that a gun decided on its own when to kill. On deck, the gunners looked at each other in disbelief. In the exercises, nothing had compared to that. Before, it was enough to miss by a few meters to waste a whole shot. Now, it was enough to be close. The projectile did the rest. The Japanese didn't notice anything. For them, it was another successful shot. But behind the scenes of the American fleet, the alert was triggered. The device worked. In a real environment, under tropical heat, with naval vibration, electromagnetic noise, and terminal velocity, the prototype had proven its worth. And the after-action report was unambiguous. 4 planes shot down, 3 of them without direct impact. The number of rounds needed per target had dropped by half in a single day. For engineers on the ground, it was the equivalent of watching the first light bulb go on after years of theory. For the Navy, it was the birth of a new kind of defense. The USS Helena didn't just test the fuse, he redefined the role of naval artillery. Up to that point, ships were essentially passive in the face of air attack. Their defenses were dense, noisy, and often ineffective. Each aircraft shot down cost hundreds of shots. Now, a few were enough. And most importantly, the reaction time had decreased. The intelligence of the projectile compensated for human failures. The surprise factor, so valued by the Japanese, began to crumble. Kamikaze tactics, still under development, would be deeply impacted by this new invisible barrier that now enveloped Allied ships. The U.S. Navy, realizing the potential, moved with speed. Pacific Command required additional batches. Priority was established. Each cruiser and battleship would receive ammunition with proximity fuses under strict use and handling protocols. Only a select number of officers were authorized to unlock the weaponry. The secrecy was absolute. Because if the Japanese found out too soon, they could try radio jamming countermeasures or, worse, capture and replicate the technology. The watchword was clear: use, but not explain. The following weeks confirmed Helena's data. Other ships equipped with the new armament began to report hit rates that were previously unthinkable. Some engagements saw anti-aircraft artillery reach 80% efficiency. The skies, once the domain of diving attacks and night squadrons, became risk zones for enemy pilots themselves. A new doctrine was quietly emerging. It was no longer necessary to see the enemy. It was enough to detect it. The ammunition would do the rest. Meanwhile, in Japan, reports of losses mounted, but no one knew why. The pilots reported that they were being hit before completing their attack routes. The hypotheses varied: better training of the gunners, firing radar, luck. No one thought that, for the first time, the projectiles had become hunters. The war, without fanfare, entered the era of autonomous decision. And the USA, with its factories hidden in the countryside, with its workers with thin gloves and eyes attentive to the microscope, had laid the first stone of this new era. Success at sea has led to the inevitable question on land: what if this also works on the ground? Because if the sky could be defended by thinking ammunition, perhaps the trenches could also be protected. The next target, the field artillery, and with it, one of the bloodiest battles of the century, where the frozen sky of Europe would be crossed by explosions that would never touch the ground. In the months following the successful test on the USS Helena, what was an experimental secret quietly became the backbone of American naval defense in the Pacific. The Navy, convinced of the efficiency of the new device, authorized full-scale production and unrestricted use of proximity fuses in all frontline units. From then on, every American battleship, every cruiser, every destroyer began to operate with ammunition that it thought, and the impact was as sudden as it was definitive. Instead of intensifying fire to compensate for poor accuracy, the ships now saved ammunition and magnified the damage. Radio-controlled drone tests were conducted in secret in the Marshall Islands, where remote-controlled aircraft simulated attacks on vessels. The data was consistent. VT fuses increased the first attempt kill rate by up to 75%. In night simulations, they reached levels of precision previously considered unattainable, even without eye contact. The defense doctrine has changed. The focus is no longer volume of fire and has become quality of shooting. With each missile launched, the enemy's panic grew. The skies now belonged to calculation, not instinct. In June 1944, this transformation materialized in brutal fashion in what would become known as the Great Mariana Firefight, the Battle of the Philippine Sea. Japan, still convinced that its naval aviation could dominate the Pacific theater, launched a massive attack. 423 aircraft, including fighters, bombers, and torpedo bombers, took off from its bases and aircraft carriers toward the American fleet. They expected to meet conventional resistance, spinning guns, late explosions, human failure. They found something else. An invisible wall of fire, coordinated by radars, operated by smart munitions. In less than 12 hours of combat, 315 Japanese planes were shot down. The sea was covered in debris, bodies, and burning oil. The surviving pilots described the same phenomenon. The explosions happened before the target was in range. Without warning, no impact, no way. What the Japanese called an honorable decision, a frontal assault based on courage, was suddenly reduced to a ritual of annihilation. Torpedo boats, which had previously been able to break through formations with low maneuvers, were hit while still on the rise. The bombers, when diving, did not line up the target. The U.S. Navy was no longer just a reactive force. It became predictive. It was like fighting an opponent who saw in all directions and shot before being seen. Technology anticipated action. For the first time, kamikaze doctrine began to gain traction among the Japanese military, not out of faith, but out of desperation. The pilot would no longer have a chance to drop his payload and escape. Then it became more useful to crash straight into the target. Allied technology, paradoxically, created a moral distortion in the enemy. Since they could not win accurately, they would seek chaos. In the rear, the logistical effect was equally decisive. Ammunition consumption dropped, the efficiency of each ship increased, and the pressure on supply convoys decreased. Freighters that once carried thousands of tons of ammunition to maintain the rate of fire now carried less and fueled more ships. The American logistics chain, already robust, has become lighter and more agile. The calculation was relentless. A ship equipped with VT fuse needed 40% fewer shells to ensure its defense against an air attack. This freed up room for more fuel, more food, more attack armaments. It was the mathematical war won with brutal elegance. Japan, even observing the results, did not understand the nature of the change. Its internal reports credited American effectiveness to a new kind of firing radar, or luck. They had no idea that the secret was inside the munitions, not in the conning towers. In Tokyo, as engineers sought to improve engines and design new fighters, the Allies were already producing 70,000 units of proximity fuses a day. The distance between the powers was no longer just technological, it was philosophical. While the Axis empires still bet on heroes, the Americans bet on sensors. And in war, the one who thinks faster wins. On the American bases, morale has been transformed. Sailors who had previously fired volleys in the dark now saw results. Crews, once hostages to the unpredictability of airstrikes, have become confident, and trust spreads. It builds momentum. Superiority is no longer theoretical, it becomes visible, measurable. The skies of the Pacific have changed hands, and anyone flying against the United States knew that at some point along the way they would be detected and destroyed. In the midst of this new balance of power, one detail changed everything. In July 1944, a Japanese plane was shot down before completing its approach turn, more than 3,000 feet away. The projectile responsible was recovered almost intact. The fragments analyzed by Japanese technicians showed unmistakable signs of electronic components. For the first time, a draft of the secret was placed on the desk of the Imperial High Command. The answer was dry. This is invention. The Americans don't have that capability. A denial that would be costly. Because, while they discredited the evidence, the United States was preparing to transfer the first batches of VT fuse to a new front, Europe. And there, in snow-covered forests and soldiers hidden among trees, the smart weapon would stop aiming at the sky, and it would start to explode above the heads. London, June 1944. The sky over the city did not herald storms, but something much more dangerous. Silence. A silence suddenly cut by a metallic, irregular mechanical sound. Then more silence. And then the explosion. It was the standard of the new German threat, the V-1 flying bombs. Known as buzz bombs by the British, they had no pilots. They did not change direction. They could not be traded. They just flew in a straight line until the engine stopped, and then they crashed. Hitler called them Wunderwaffe, wonderful weapons. To Londoners, they were just impersonal death from heaven. Traditional defenses could do little. Fighters had difficulty intercepting objects without a pilot, and artillery, with time fuses, rarely exploded at the right height. The success rate was meager, 24%. For every 4 V-1s launched, 3 crossed the channel and hit their targets. It was a timed massacre. Churchill, pressured by the war cabinet and the exhausted population, which had already survived the Blitz, did the unthinkable. He authorized the use of the new proximity fuses on British soil. Until then, the device was considered too top secret to operate in territory subject to invasion. But the situation required risks. The first battery of 90mm anti-aircraft guns equipped with the new fuse was positioned at Kent. And on the first night of operation, the difference was brutal. The explosions no longer missed the mark. They found the target. In 2 weeks, the V-1 slaughter rate jumped from 24% to 79%. And that changed everything. The morale of the population, the course of the attacks, and the German perception of what was really happening. The Germans, as usual, sought explanations within their own logic. They suspected a new type of sight. Then cannons with improved rate. Some have even considered the use of electromagnetic interference. But no one even imagined that the shells had been made intelligent. The answer was there in the bowels of American technology, but its simplicity was, for the Germans, inconceivable, because it was not a spectacle weapon. It was a precision weapon, invisible and systematic. This is where a fact emerges that the Germans simply ignored or did not want to believe. By 1944, the United States was producing 22 times more anti-aircraft shells than the entire German arms industry combined. That's right, 22 times more, and with a hit rate of over 70%. If you were also surprised by this number, write in the comments. Logistics wins, because victory at that point in the war was no longer a matter of bravery or tactics. It was an equation of production, science, and delivery. The V-1s continued to fly for a few more weeks, but now their paths were shortened, their explosions deflected, and their effects drastically reduced. Hitler's impersonal terror had met, ironically, its defeat in the technical humanity of Merrill Tuve and the American engineers. What was once inevitable was now preventable, and what seemed like an unbeatable attack was transformed in weeks into a failure statistic. The city Hitler swore to erase turned its lights back on, not as a provocation, but as a statement. There was a new kind of shield over London, a shield built with silicon, calculus, and steel. In the German High Command, the bewilderment grew. Cross-information pointed to new weaponry, but the details were vague. Intelligence reports mentioned aerial fragmentations, damage caused without direct impact, early explosions. A Luftwaffe officer visiting the wreckage of a downed V-1 commented confidentially, "They're not just shooting, they are seeing." The phrase was recorded in an internal memo, but treated as emotional exaggeration. After all, no ammunition could see. That was science fiction, or was it? And if the skies of London could be protected in this way, why not the fields of Europe? Why not the frozen trenches of Belgium, where American soldiers, days later, would face the last offensive gasp of the Reich? The answer, as always, would come from above. But it wouldn't fall to the ground. It would explode before that, exactly where it should. December 1944. Dense forests, sub-zero temperatures, grey skies, and exhausted soldiers fighting for every hill. The Ardennes offensive began, the last major German attempt to reverse the course of the war on the Western Front. For the commanders of the Third Reich, it was a matter of repeating the miracle of 1940, crossing the Allied lines with surprise, speed, and brutality. For Americans, it was a shock. The initial German advance caught entire units off guard, cutting off supplies, encircling battalions, and spreading chaos. But what Hitler's generals did not know, and would soon learn with horror, was that this attack had unwittingly triggered the first large-scale ground application of a new type of munition, one that did not respect the old rules of war, one that thought. Colonel William E. Axelson, artillery commander in support of the 2nd Infantry Division, watched with frustration at the maps and reports. German troops concentrated in clearings, used valleys for cover, repeated tactics that for centuries had worked against impact cannons and time shells. The official order was clear. The new VT proximity fuses were not yet authorized for use on land. The risk of capture was too high. But Axelson, faced with the real threat of collapse of his line, made a quiet decision. Without consultation, he began to order that all firing from the batteries under his command be loaded with secret shells. The shells no longer look at the ground. They started to explode in the air. The effect was immediate and devastating. Unlike conventional explosions which burst into the ground and allowed soldiers in trenches to escape with their lives, the new projectiles exploded between 5 and 15 meters above the ground, where the impact was lethal. The trees amplified the fragmentation. The roof, which previously offered shelter, became a trap. Entire platoons disappeared under a rain of metal shrapnel designed to maximize lethality in 360 degrees. German veterans, accustomed to withstanding bombing raids and advancing just past silence, were caught off guard. There was no more silence. There was no more security, just the sound of shells that never touched the ground and killed before anyone could duck. The reports that reached the Wehrmacht headquarters bordered on incredulity. A battalion commander reported that his unit had been decimated by unseen gunfire. Another, that the explosions came from heaven as the last judgment. Many thought they were aerial mines. Some suggested that the Americans were using invisible planes. The truth, as always, was simpler and more brutal. The artillery had learned to think, and when the artillery thinks, there is no doctrine that survives. Aselson's breach of protocol was, days later, analyzed by the American High Command. But instead of punishment, the gesture yielded a report from General Patton, who arrived at the General Staff with a direct phrase, "This ammunition is magnificent." The approval became retroactive. Batteries across the Western Front received full authorization for use of the VT fuse. In less than a week, what was the exception became the rule. And war, once again, changed its nature. Gunners no longer needed to know the exact position of the enemy. It was enough to shoot the sector. The projectile itself was in charge of seeing where the target was. As fighting escalated in the Ardennes, the numbers began to be tabulated, and the numbers spoke loudly. Units equipped with the proximity fuse had twice the fire efficiency. The amount of shells needed to neutralize a position dropped dramatically. Most importantly, the ability to disorganize enemy concentrations in the open was tripled. The Germans, who were counting on fast movement and surprise, began to hesitate. Every group of soldiers, every transport, every artillery on the march was a potential target, even before it fired. German doctrine, based on centuries of field study, collapsed in the face of a variable that was not included in the manuals. The intelligence incorporated into the projectile, the ambush tactics, the hidden defensive lines, the fog-shrouded advances, everything became irrelevant. The new ammunition did not need to see. She felt it. The internal radar measured distance and detonated with millimeter precision. The concept of margin of error has been removed from the battlefield. The result was so lopsided that an SS officer captured days later at Bastogne declared, "Your cannons are possessed. They shoot, and death falls from above. There's nowhere to hide." The interrogation was recorded and sent to American intelligence as proof that the enemy was finally beginning to understand. Too late. Because, while the Germans digested the shock, the American production machine was already delivering new batches adapted to different calibers and conditions. The weapon had proven not only its effectiveness, but its adaptability. And that was the real terror. There was nowhere else for Germany to fight in advantage. Neither at sea, nor in the air, nor under the frozen land of the Ardennes. And if the artillery could think, what else were Americans about to teach their guns? The answer would soon come, in a place where there were no trenches but kamikazes, and where the only salvation was in the exact time between an internal radar and the end of the world. Between 1944 and 1945, a new form of fear took hold among the German and Japanese ranks. It did not come from tanks roaring in the distance, nor from planes tearing through the skies. It was the fear of silence. A silence broken only by the thin, growing sound of something invisible, the whistling of a projectile that was not coming to hit the ground, but to explode above the head. The accounts began to pile up in the diaries and intercepted letters of Axis soldiers. Experienced men, veterans of Stalingrad or Guadalcanal, wrote about a type of attack that was impossible to anticipate. They did not speak of massive bombardments, but of small artillery strikes that seemed to come out of nowhere. Some called them the ghosts of heaven. Others spoke of invisible rays. Imagination filled in the gaps that logic could not, because there was no logic, just bodies falling without a single impact being heard. The German infantry divisions, trained from their youth in the doctrine of fire and movement, found themselves paralyzed. In letters captured on the outskirts of Aachen, soldiers reported that the ground was no longer protective and that the new shells explode in the air as if they could see. On the Pacific front, the Japanese, accustomed to resisting tenaciously, began to abandon entire positions at the slightest sign of American artillery. Lieutenant Shigeru Matsuda, commander of a unit in the Philippines, wrote in his diary, "Their new artillery does not wait. She knows where we are." Matsuda was not wrong. Proximity fuses had abolished the interval between detection and destruction. To the soldiers in the camp, it was as if the Americans knew what they were thinking. Psychologically, this was devastating. The war, until then, still allowed an exchange of logic, to hide, to maneuver, to resist. But VT-fused artillery subverted everything. The penthouse, once a hope, became the sentence. The trees, the trenches, the unevenness, the rocks, all became natural traps when the shell exploded before it touched them. And worse, without standard. A shot could explode 10 meters away, another to 6, another exactly at the point where a group rested. There was no time to count, run, or regroup, just the certainty that the next bang would not be on the ground, but in the air. The impact was not limited to the soldiers in the field. Senior officers began to notice a change in the behavior of their troops. Men slept less. They reacted with panic to any sound similar to the whistling of the projectiles. Medical reports spoke of collapses without injuries, absence of response in combat, and explosive expectancy syndrome. In short, the soldiers expected to die, not knowing when, where, or why. The invisibility of the weapon made it ubiquitous. Even when it didn't fire, the fear that it might fire was enough to disorganize entire units. The effectiveness of a weapon, as American strategists knew, is measured not only by what it destroys, but also by what it prevents from happening. And at that point, the proximity fuse reached a new level. It was a weapon that killed the will to fight. German military doctrine, built on pride in endurance and discipline, began to show cracks. On the Western Front, elite units began to give way faster. An Army Group B report, dated February 1945, warned that enemy forces have developed a type of fire that anticipates our movements. Morale is severely shaken. The document did not mention the name of the device, because they didn't even know what it was. The irony was cruel. Nazi Germany had bet everything on impact weapons, giant cannons, rockets, flying bombs. They believed that fear would come from the spectacle. But what undid them was just the opposite. A weapon without spectacle, without fanfare, without signature. A weapon that did what it needed to do. And then, silence. There were no propaganda videos. There were no triumphant speeches. There were no mythological names like V2 or Dora. There was only a small radar, the size of an apple, installed on the head of a steel shell. And this apple, metallic, cold, impersonal, planted panic wherever it went. It is at this point that a statistic emerges that is difficult to ignore. Between January and March 1945, on all fronts, where the US used artillery with proximity fuses, German losses increased by as much as 60%, while American casualties decreased by 40%. A complete reversal of the Ware curve, and if you were impressed by these numbers, leave in the comments. Shocking data. Because behind this change was a brutal lesson. The war was now won in the air, even before the enemy realized he was under attack. But the Americans were not going to stop there, because while the Germans succumbed to the fear of the invisible, the Japanese were preparing something more desperate, voluntary death as a doctrine. And when courage turned to suicide, the US would respond with mathematical precision and ammunition that fell from the sky like a programmed sentence. For centuries, artillery followed the same logic: aim, fire, wait. It was a statistical science based on maps, calculations, and assumptions. The enemy attacked, and the defense responded. But between 1944 and 1945, something fundamental was reversed. With the massive introduction of radar proximity fuses, the line between defense and attack was blurred, and anti-aircraft artillery, hitherto marginal in the tactical game, became the absolute protagonist. Once a deterrent tool, cannons began to shape the battlefield, no longer waiting for the enemy to reveal himself, but forcing the enemy to hide before they even appear. For the first time in military history, a stationary weapon imposed movement on the adversary. A weapon designed to protect began to dictate the offensive pace. The first changes occurred in the outposts. With the effectiveness of the fuses confirmed, field commanders began to organize their formations no longer according to rivers, hills, or villages, but based on the radius of the new technology. A 19mm station with VT fuses became, in practice, an autonomous stronghold of deterrence. Any aircraft that crossed its coverage zone entered an almost instantaneous kill zone. This forced the Germans to alter their routes, their altitudes, and even their penetration tactics. But there was no way to beat an equation solved before the first shot. A Bf-109 flying at 500 km/h was still slower than the logic of a radar circuit with two miniaturized valves. The new doctrine spread rapidly. The batteries no longer operated only as a rear guard of the mobile forces, but began to advance in tandem with them. Artillery was now a system of continuous surveillance and punishment. Its sensors replaced human eyes. Their calculations higher than any observer's estimate. Most disturbingly, the fuses didn't just blow up near targets, they chose the best time. With a margin of error of less than 2 meters, the projectiles learned by wave pattern to differentiate between soil, tree, metal, or meat. Each explosion was an algorithmic decision in the middle of World War II. On the other end of the line, the Germans were still betting on the blitzkrieg. Rapid movement, surprise, collapse of the enemy before he had time to react. But this logic did not stand up to American science, because now, when accelerating, they just entered the fuse range faster. By trying to concentrate troops to break through the front, they offered perfect targets for aerial explosions that eliminated dozens in seconds. The blitzkrieg, which had lived off imbalance, found its mirror, a weapon that balanced everything. The surprise factor had changed hands. This transition was not only technical, but conceptual. Defense had become attack. The ammunition's internal radio decided faster than any platoon commander. In many battles, the time between the sighting of a target and destruction was less than 3 seconds, too short for maneuver, long enough for annihilation. Radar operators integrated with artillery began to assume functions previously exclusive to tactical intelligence. The sky turned to ground. The soil, trap. War ceased to be a territory of bravery and became the territory of algorithms. The impact on enemy formations was total. Troops began to operate in smaller groups, which reduced firepower. Vehicles were camouflaged with improvised techniques, ineffective against electromagnetic sensors. In certain quarters, the Luftwaffe simply stopped flying. With 8 out of 10 planes shot down before reaching the target, the order was to avoid confrontation, something unthinkable 2 years earlier. The Nazi war machine, which based its strength on offensive mobility, was forced to a standstill, and a standing army is a defeated army. The irony of it all is that the Americans were not looking for a weapon of domination. They were looking for a solution to the chaos of modern warfare. But what they created was, in fact, a new type of combat. One where human senses were replaced by radio waves, where courage was insufficient, where the doctrine became obsolete within weeks. General Hodges wrote in March 1945, "The front today is defined by technology. The enemy still thinks in terms of geography. We think about reach. A sentence that unintentionally summarizes what had happened. The battlefield changed owners. The result? In less than 6 months, positions with artillery equipped with VT fuses suffered 65% fewer losses. And they didn't just repel attacks, they drew the enemy into predetermined zones of destruction. Like invisible bait, these positions became breaking points for the Allied advance. Control of the sky, sound, and time was in the hands of those who dominated the circuits. It was no longer the force that won, it was the frequency. But the most brutal moment was yet to come, because if the projectiles could think, and if they could choose the ideal moment to explode, there was one last frontier to be crossed, that of calculating not only the distance, but the enemy's own destiny. And that fate would, ironically, pass through a missile that Hitler considered invincible, and that the Americans were about to shoot down before it even reached its zenith. April 1945. Okinawa, the last stronghold before the Japanese archipelago, became the biggest stage of despair and technological decision of the war. For the Japanese Empire, it was the end of the map. For the United States, the beginning of the last act. On the Japanese side, the strategy was clear. Attack with what was left, and what was left was meat, steel, and sacrifice. More than 2,500 kamikazes were launched against the American fleet over the course of 3 months. Young pilots with farewell notes strapped to their uniforms and planes, laden with explosives, plunged toward the ships with the promise of glory. The objective was simple: to cause panic, break formations, sink morale. But what they found was not chaos. They found logic. They found artillery that he was thinking of. Around the islands, a dense web of invisible destruction had already been woven. Every battleship, from destroyers to battleships, now operated on projectiles equipped with proximity fuses. It was a mathematical network. The Bofors and Oerlikon's automatic weapons, synchronized with short-range radars, fired shells that detected the target within a few meters and detonated at the ideal moment. A single shot could fragment a suicide fighter before it crossed the line of attack. But it wasn't a miracle. It was the end product of 3 years of applied engineering, lab testing, mass production, and human-machine integration. The ships, once fixed targets, had become floating digital fortresses. The result was brutal. Of the more than 1,500 kamikazes launched, about 1,100 were shot down before reaching any targets. This meant that 75% of Japan's sacrificial force was simply dissolved in the air. Those who managed to break through the curtain of fire still faced multi-layered defense systems, each controlled by sensors and algorithms. What the pilots expected to find, slow ships, panicked sailors, chaos, didn't exist. Instead, each attack was met with a precision wall, where the response time was less than the human maneuver time. War was no longer driven by emotion. It was programmed. The U.S. Navy's reports on Okinawa reveal the complete transformation of the naval battlefield. In one operation, the USS Laffey was attacked by 22 kamikazes in less than an hour. Knocked down 9 before impact. Survived. Not by chance, all the shots recorded used ammunition with VT fuses. One statistic ignored by the Japanese High Command before the offensive was telling. By early 1945, the US had produced more than 22 million proximity fuses. Germany, on the other hand, had not been able to develop even a functional prototype. A difference not only in capacity, but in paradigm. And if this data surprised you, comment, "Logistics wins." With each new day of the battle, the Japanese discovered that courage was not enough. The sky, once a space of tactical domination, had been hijacked by mathematics, and there was no way to face it. Pilots trained for months to fly close to the sea, avoid radar, dive at unpredictable angles. But no angle escaped a circuit that detonated when it recognized an approaching metallic mass. The accuracy was such that many planes exploded even before entering the gunner's field of vision. The defense, for the first time in history, saw before being seen. The impact was not only military but moral. Japan, which had built its war on the mythology of sacrifice and honor, was faced with an enemy that reacted not with fear, but with calculation. The American logic was cold, but efficient. Each suicide attack was answered with applied science. For each pilot with a scream, there was a radio frequency valve ready to silence him. It was the collapse of military romanticism in the face of serial engineering. And Okinawa sealed this turnaround. There was no more glory in the attack. There was only predictable death, and that was unbearable for a culture that turned every thrust into a ritual. Even so, Japan continued. Not out of hope, but out of desperation. Every day, more wooden and fabric planes were adapted for suicide missions. More improvised fuels, more volunteers. But none of this changed the tactical picture. With each new attack, the statistics were maintained. And in the end, it was with them that the Americans decided their next steps. Admiral Spruance summed up the new paradigm of warfare in one sentence. Let us come. Our calculations are better than your faith. But what the Japanese didn't know, and the world hadn't yet understood, was that this technology, developed in secret to protect ships and shoot down fighter jets, was about to take on a new role. A role that had nothing defensive about it. Because if a projectile could think, perhaps he could also guide, and what would come after Okinawa would not fall from the sky by chance, but by decision. A decision made thousands of meters high, scheduled, cold, and final. World War II was characterized by a series of technological innovations that in many cases changed the course of the conflict. But one of the most secret, and possibly the most decisive, was the development of proximity fuses, an invention that not only destroyed enemy planes in the sky, but also dismantled the entire strategic structure of the Axis powers. However, the most surprising thing about proximity fuses is not their effectiveness in battle, but how much their development has been kept in absolute secrecy. Even President Harry S. Truman, when he took office in 1945, was unaware of the existence of this project. In direct contrast to the Manhattan Project, which involved a large mobilization of scientists, engineers, and more open communication, the Proximity Fuse program was conducted with such an intense level of secrecy that only a small number of people in the White House knew of its existence. In fact, only about 10 individuals in high-trust positions within the US government were aware of the magnitude and progress of this secret project. Not even the generals closest to Eisenhower, such as George Patton or Bernard Montgomery, had access to details of this technology. Secrecy was absolute, and his safety was treated as a matter of life and death. The operational protection of the fuses was almost paranoid, while the atomic bomb, with its devastating power, was a visible symbol and an object of study for enemies. Proximity fuses operated in the shadows. The program was decentralized in such a way that no single scientist or engineer had complete knowledge of the manufacture or use of the fuses. Each part of the device was produced in different locations and, in many cases, in companies without knowing exactly what they were assembling. The pieces went through an extremely rigorous physical tracking process. Each component, before being used, had a self-consuming label, which prevented any form of reconstitution or tracking if it was lost or stolen. Project-related documents were destroyed daily, and more draconian security measures were implemented at each stage of production. This generated an interesting paradox. Although the Manhattan Project attracted global attention, with scientists such as Robert Oppenheimer and Enrico Fermi being public figures, the Proximity Fuse program remained in the dark, a ghost of military technology. A ghost that no one could study, no one could intercept, and crucially, no one could replicate. The reason for this caution was simple. The US knew that if Germany or Japan had managed to get their hands on proximity fuses, the game would have changed dramatically. Not only would the Allied tactical advantage have disappeared, but the real revolution of modern artillery, with its aerial bursts and impact selectivity, would have been reversed. While atomic bombs were imposing and destructive, proximity fuses were discreet, invisible, and highly effective. They were not only altering the way the Allies fought in the sky or on the ground, but they were redefining the very nature of warfare. A war no longer fought by brute force, or only by weapons of mass destruction, but by precision, engineering, and time. War now was a matter of understanding patterns, predicting movements, and programming responses. What the Germans, and to some extent the Japanese, underestimated was precisely the ability of the United States to keep secret about an innovation of this magnitude. Despite its own industrial might, Germany has never been able to compete with the US. Ability to mobilize its infrastructure in a coordinated and secretive manner. Try as the German engineers might, they could never muster the talent needed to do what the Americans did in a matter of months. Technological distance was not just a matter of knowledge, it was a matter of mobilizing and protecting innovation. This absolute secrecy, in part, was one of the most decisive factors in the success of the fuses. While German scientists at the height of the war effort were just beginning to understand the principles of proximity fuse technology, the Americans were already in full production and operational use. The Nazis, even with their own advanced radar and explosives designs, were never able to achieve the miniaturization, reliability, and speed of production that the Americans were implementing. And when, finally, the Germans managed to capture some of the proximity fuses, they concluded that they were simple inventions that were impossible to replicate. They were, for the most part, right. The level of sophistication of the technology, coupled with the secrecy surrounding it, made the weapon virtually insurmountable. What to the Germans seemed like a simple piece of ammunition was actually a combination of cutting-edge physics and industrial production engineering that was ahead of any capability they could muster. And most ironically, what Americans regarded as a secret weapon was actually one of the most successful victories of the war, not because of its brutality, but because of its precision. Technology didn't just save Allied lives, it imposed a new order on modern warfare. Without the logistical or operational difficulties faced by Allies, without the need for vast quantities of ammunition or nuclear bombs, proximity fuses became the greatest example of how technical innovation could trump brute force. This story, however, still holds many secrets. As part of this strategy of secrecy, the success of the fuse program was kept hidden even after the war ended. Many of the reports and documents only became public decades later. The real impact of this technology, both in the battles in which it was used and in the revolution of defense concepts, is a mystery that has yet to be fully unraveled. For now, the biggest lesson that remains is this: modern warfare is no longer defined solely by the ability to resist an invasion, but by the ability to make technology work in its favor invisibly. And in the end, whoever controls the innovation controls the future. And the next battle, which was yet to come, would show us how much the war was already being decided, not on the battlefield, but in the factories and laboratories of a country that understood that true strength is not only in weapons, but in the engineering of the fastest responses. In 1944, in the midst of the Battle of the Bulge, German forces were advancing with their strategy of penetrating through the dense forest, imagining that their tactical superiority would be enough to break the Allied line of defense. But amid the chaos of the conflict, a discovery that should have been a deadly warning went unnoticed. German troops captured several American artillery shells with the proximity fuses still intact and sent them back to Berlin for analysis. What followed was an emblematic moment of strategic and ideological blindness. Upon examining the devices, Luftwaffe engineers quickly dismissed the shells as unviable. According to them, the mechanism simply could not work under the extreme forces to which fuses would be subjected when fired from a cannon. In reality, they were so committed to the idea of their own technological superiority that the mere notion that the Americans could have developed a weapon with such advanced precision and ingenuity was, for them, unthinkable. Germany's technical arrogance was, at that time, one of the greatest obstacles to the survival of its war machine. They were aware of the American advance in terms of industrial production, but they couldn't even imagine that technological warfare was becoming a battle of precision, not just brute force. The Nazi high command, obsessed with the idea that innovations coming from the Axis were superior, simply refused to accept that the United States had surpassed Germany in technological precision and military innovation. When German scientists in Berlin looked at the project, they saw a simple, miniaturized radar device. But what they didn't see was the impact that this miniaturization would have on the way war would be fought. The first reaction of the German command was to ridicule the idea of a smart fuse. How could the Americans, in the midst of World War II, overcome the superiority of German design and engineering? The thought was simple. That can't be possible. As much as German engineers studied, tried, and even produced alternative prototypes, the innovation and production capacity of the United States was unparalleled. The closed mentality of the Luftwaffe, unable to see beyond its own worldview, led Germany to a fatal denial. And ironically, that same blindness led the Allies to a quiet victory, a victory that was forged in the factories and laboratories of the United States rather than on the battlefields. While German engineers dismissed American technology as impossible, the world around them was beginning to change. Within weeks, Allied forces would be using proximity fuse shells in devastating ways in combat trenches, while German officers refused to accept what was happening before their eyes. And what the Germans missed most was the fact that by underestimating the effectiveness of this innovation, they would not only lose a decisive strategic advantage, but they would also witness the collapse of the tactics that had worked so efficiently up to that point. The Allies, on the other hand, were benefiting from this innovation. At a time of pure military and logistical ingenuity, the US had in its hands the first smart weapon in history, a simple but lethal project with an impact the Germans could not foresee. When the proximity fuse exploded over the heads of the German soldiers, it was not only the enemy's stomachs that churned, but the very military doctrine they had followed for decades. German arrogance, the same one that disregarded the difficulties of protracted war and overcoming industrial failures, also ignored the power of an industrial model that not only produced the most advanced technology, but also had the ability to turn that technology into a weapons system on an unprecedented scale. In reality, what the Germans had in mind was a war of speed, of blitzkrieg, in which strength was synonymous with victory. What they didn't see was that the war was changing. Weapons would no longer only be designed to destroy, but also to think, calculate, and decide. And this thought, symbolized in the proximity fuse, began to gain ground. The underestimation of the industrial capabilities of the United States by the Nazi high command represented a critical failure in the analysis of how modern warfare would be fought. The command not only disregarded the superiority of American production, but ignored the ability of Allied forces to develop and employ new technologies with impressive speed. By comparison, Germany, despite its advancement in areas such as aircraft engineering and V-2 rockets, lacked the industrial base necessary to turn its concepts into measurable and sustainable combat power. And this strategic error was not limited to the military field. The underestimation of the logistical power and adaptability of the Allies ended up creating a huge perception gap among German leaders. They believed that by controlling the pace of the war and maintaining an aggressive approach, they could win. However, what they didn't realize was that the real strength was in adaptive innovation, in the power to manufacture and deliver not just weapons, but innovative solutions that exceeded all expectations. Germany was dealing with a war of mass destruction, while the Allies were, in fact, fighting a war of precision, driven by invisible data and algorithms. When Allied forces began to use proximity fuses effectively in Europe, the irony was palpable. The Germans, who had captured the technology, were now about to experience firsthand what they had so contemptuously rejected. Proximity fuses would begin to impact his troops irreversibly. Fortifications and trenches, which had been symbols of impenetrable defense during World War I and II, were now vulnerable targets for technology that the Germans considered impossible. General Patton himself, witnessing the destruction these shells wreaked in the Ardennes, wrote to the US High Command, "This ammunition is magnificent." The war had changed, and the Germans, with their ideological blindness, were now at the mercy of a weapon they had never imagined possible. What happened after this initial reaction from the Germans is a story of historical underestimation and irony. The Luftwaffe High Command, in dismissing the idea of a smart weapon, made a fatal mistake. The technology they ignored in 1944 would not only become one of the most effective in modern military history, but it would also show how warfare was evolving, not just in terms of weapons, but in the very way nations fought their conflicts. The future of warfare was being drawn not on the battlefield, but in secret laboratories and mass production factories. That moment, when Germany had the gun in its hands and chose to ignore it, signaled one of the greatest technological ironies of the war. The same engineers who had mastered artillery and aviation were now being overtaken by a seemingly simple but profoundly revolutionary innovation. And while German arrogance continued to grow, the real force of the war was in the hands of those who knew how to use technology to change the game in irreversible ways. In the silence of America's factories and laboratories, far from the battlefields, a group of scientists and engineers became the decisive force behind the war. They were not celebrated heroes, nor did they possess medals or honors, but their names would forever be linked to a radical change in the way military conflicts would be fought. They were the men who thought like machines, whose minds, rather than weapons, were their greatest tools. Many were young, idealistic, Jewish refugees, civil engineers and others with skills from different fields of science, but united by one mission: to create something that could save lives while facing the immensity of war. These scientists were not on the battlefield, but their work was as crucial as any battle fought at the front. Instead of trenches and explosions, their battlefield was made up of mathematical formulas, complex calculations, and senseless testing. Each mistake, each wrong formula meant one step further from saving a life. While soldiers on the front lines fought with rifles and tanks, these men were fighting against time, against the limitations of the technology of the time, and against the very limits of their physical and mental strength. The nights were long and exhausting. In a moment of critical failure, one of the engineers was blinded after an experiment with explosives. Another, overwhelmed by pressure, died of exhaustion. They were often on the front lines of the quietest and equally deadly battle facing the United States, the war for innovation. The conditions were harsh. With each failure, they faced the weight of knowing that the cost would not be measured in simple numbers, but in human lives. Their mission was not only to win a war, but to save as many people as possible, and that required an immeasurable level of dedication and sacrifice. There was no room for distractions or doubts. Every advance, every discovery became a promise of protection for those who were facing the horrors of war on the battlefield. What many did not see was the despair in the eyes of these scientists. They were not just technicians or researchers. They were men who believed deeply in the morality of what they were doing. With every line of code written, with every circuit created, There was hope that they could finally deliver a solution that would change the course of the war and preserve lives. They were creating a weapon that would not be visible on the battlefield, but its impact would be felt in every corner of the world, especially in the trenches and in the air, where the war was being fought most brutally. But this journey was not without sacrifices. Each victory in the laboratory was won with pain and effort. Behind the formulas and experiments were human beings with their weaknesses, fears, and limitations. And yet, they persevered. Many of these scientists, whose names would be forgotten or overshadowed by the grandeur of the war's events, were responsible for something that did, in fact, help change the course of history. They weren't thinking about fame or recognition. They were just trying to solve the impossible because they knew that humanity depended on it. His work was, for many, invisible. Although the weapons they designed were the decisive factors in the victory of the Allies, the scientists behind this invention were not prominent figures. They were far from the front, but their work was being forged in the shadows, without applause, without a cheering crowd. And yet, it was their minds that were truly at the center of the modern warfare revolution. His innovations became the key to the defense, strategy, and survival of thousands, if not millions. The victory that the Allies won was not only the result of the bravery of the soldiers, but of the unbeatable science and ethics of these invisible heroes. But these scientists were aware that every advance was actually a moral burden. The ethics behind his work were not just to invent something to destroy, but to create something that would protect lives in a more efficient, smarter way. Artillery would no longer be just an instrument of destruction, but a precision tool designed to save, not just kill. For every night of work behind closed doors, there was a promise of peace and hope. The technology they were developing was not like any other. It was, in fact, a quiet revolution. Quiet. Not only because proximity fuses were weapons that could change the course of warfare, but because their creators, never knowing if their inventions would be successful, knew they were doing more than simply fighting an enemy. They were creating a new way of fighting, a method where intelligence and innovation would intertwine with morality and sacrifice, giving war a new face and possibly a closer end. And while war was a physical and bloody battlefield, scientists were fighting a much more complex war, where every right formula and every failure could decide not only the outcome of the war, but the future of all nations. The irony of this story is that the solution was in front of them. If you're enjoying unraveling these facts, show your support. Like and subscribe, so we can bring you more in-depth content about how the invisible scientists of the Proximity Fuse project helped save lives. This is one of those moments when the truth is written in science, and the future is decided in formulas and calculations. But what would come next is even more striking. The impact of the work of these invisible heroes on the larger stage of war. In the next chapter, we'll reveal the tipping point, the moment when precision warfare was no longer a concept, but a reality. And at that moment, the real technological revolution on the battlefield would happen. War, with all its brutality, has always been a field where ideological contrasts clash in a more visceral way. On the one hand, the cult of force, the obsession with racial supremacy, and the belief in a victory forged through fanaticism. On the other, a more rational and strategic vision, which believed that science could not only win, but save lives, preserving what was left of humanity in the midst of chaos. In this context, the Proximity Fuse, the revolutionary American weapon, has become more than just a military tool. He symbolized the moral superiority of an approach that did not seek to destroy en masse, but to reduce suffering and loss of life with precision. While the Germans and their allies surrendered to the power of indiscriminate destruction, the United States, with its technological innovations, followed a more calculated, more humane, more precise path. Mathematics, which has always been at the heart of science, has become the lifeblood behind this new kind of warfare. Unlike the methods of massive bombing and indiscriminate attack, proximity fuses represented a paradigm shift. They were not weapons aimed at killing more, but weapons aimed at killing better, or more precisely, killing at the right time, avoiding the prolongation of a slow and unnecessary death. The impact of this was not only reflected in the number of lives saved, but also in the way the war was fought. The science that drove the development of these weapons was applied in a way that aimed to minimize damage and prevent unnecessary loss of life, an approach that contrasted sharply with the brutal methods employed by the Nazi and Japanese imperialist regime. The proximity fuse was a concrete expression of this philosophy. The idea behind it was simple but revolutionary: to make artillery rather than simply firing at a target and hoping that the impact would cause destruction, to be able to think for itself, deciding the exact moment of its explosion. This not only made the attacks more effective, but also cleaner, in the sense that fewer ammunition was needed to achieve the same goal, avoiding indiscriminate killing and sparing as many lives as possible. Every explosion in the air, at exactly the right moment, was a victory of precision over brutality. It was science being applied with a clear purpose, no longer to cause immeasurable destruction, but to reduce suffering. Meanwhile, on the German side, the ideology that permeated the Nazi high command and its armed forces was a direct reflection of a thought that saw itself as superior, a cult of racial purity and brute force. For the Germans, the war was a test of power, of destruction, and the idea of using science in such a controlled, technical way to minimize damage was inconceivable. When the proximity fuses were captured and analyzed, many Luftwaffe engineers dismissed them with disdain, not understanding that they were facing a real revolution in the way of waging wars. The idea of a projectile that chose the moment of its explosion, which ceased to be just an instrument of death and became a tool of controlled precision, was beyond the comprehension of the regime. For the Allies, on the other hand, this approach represented a commitment to morality in times of total war. Efficiency became ethical. Rather than exploiting war as just a machine of destruction, American scientists and military personnel were using the latest in technology to ensure that victory did not come at an even greater human cost. The idea of using science to reduce losses, to avoid unnecessary deaths, was in line with the core values of Allied democracies. War, brutal as it was, should have limits, and morality should at least be tried. This is where the real ideological battle of the Second World War lies, the struggle between totalitarianism and freedom, between unbridled destruction and strategic rationality. The proximity fuse was not just a military innovation, but a symbol of the ethical superiority of the Allies over their enemies. He proved, in a practical way, that reason and science, when applied with a human purpose, can be more powerful than any mythology of racial purity, any notion of territorial conquest, or any blind will to destruction. The impact of this weapon was not only military. He was deeply philosophical, questioning the foundations of what was considered an attack and what represented a true victory. The war was not won only with courage or number of deaths, but with precision, with control. The exact moment of an explosion, rather than a wave of blind destruction, represented a change in the way conflicts would be thought of and fought from that point on. Mathematics and science, instead of simply arming forces, came to be seen as tools of containment, of intelligence, of a form of war that, in the end, aimed to preserve more lives than to destroy. The irony of this story is that the solution was, in a way, in front of the Germans. They were so fixated on their ideology of racial strength and purity, so confident in the superiority of their war machinery, that they failed to see the depth and power of what the United States had achieved with science. If you're starting to see the twists and turns of this story, like and subscribe so we can continue to explore how an invention, born of rationality and teamwork, altered the course of war in a definitive way. What follows is an even deeper delving into the implications of this moral and technological triumph. After the end of World War II, the world not only reorganized itself politically, but also began a technological revolution that, in many ways, had its roots in the invisible innovation that changed the battlefields. The proximity fuse, with its ability to change the course of the war, did not disappear with the victory of the Allies. Instead, it became the basis for the future of modern warfare and, interestingly, for the technological revolution that would come to shape the digital age of the 21st century. What began as a tiny component, an apple-sized piece of artillery, was the starting point of a series of innovations that went far beyond mass destruction. They gave rise to modern defense systems, the precision of guided missiles, and even the microchips that power the devices we use in our daily lives. The impact of the proximity fuse was direct and profound. It served as an inspiration for the development of key technologies during the Cold War, including guided missiles and nuclear warheads, which redefined the dynamics of military power in the post-war era. The miniaturization of technologies, which began with the fuse, led to an advance in precision devices which, in turn, paved the way for the automated defense systems that dominated the battlefields in the late 20th century. More effective and more lethal, but also more controllable. And paradoxically, the revolution was not limited to war. When engineers began working with the miniaturization and precision technologies that emerged from the development of the proximity fuse, the same techniques and ideas began to be applied in the world of computing and electronics. The miniaturization that began with the creation of proximity fuses directly fueled the microchip industry, which today is the backbone of the digital world. The same technology that turned the tide of a world war also opened the door to the digital revolution that would transform every aspect of human society. The modern technology industry, from computers to smartphones, from artificial intelligence to data networks, has relied on the same innovations that emerged from research done in war labs. If the atomic bomb is often remembered as the final milestone of the ancient era, a representation of the end of conventional warfare and the birth of a new kind of destruction, the proximity fuse represents, paradoxically, the birth of the future. It was not an end, but a beginning. Its influence extended far beyond the battlefields, shaping the direction of modern warfare, but also of global technological development. What seemed like a simple and affordable piece of artillery, an invention used to kill more effectively, ended up shaping the foundations of a new world, where innovations were not just physical but digital, where components that seemed made for death were actually the key to the life of a technologically interconnected future. The irony, then, is evident. While the proximity fuse was a precision tool designed to destroy, it also became the basis of technologies that enable the building, enhancement, and creation of a new world. Where warring countries saw their strategies being reshaped by the precision of science, post-war science saw that same science spawn a more connected, more advanced, and in many ways more interdependent world. What began as a war solution ended up as the foundation of a new era, the digital age, driven by precision, miniaturization, and most importantly, the revolution that the proximity fuse started. And most surprising of all, this was not an accident. It was the power of science, technology, and human ingenuity applied to a military context that inadvertently laid the foundations for a completely different future. The Cold War, with all its tensions and challenges, was just the beginning. The full impact of this development, even more significant and comprehensive, would unfold in the following decades. And as the US moved toward technological leadership, the shadow of a Cold War now became a war for innovation, where once again science, precision and technology were the real weapons of the future. Now, imagine the power of the proximity fuse on a battlefield. Imagine how it transformed air, land and naval combat. But what happens when this technology joins something even bigger? In the next chapter, we'll explore how, finally, the power of precision, coupled with the technological revolution, would transform the nature of warfare and the world forever. The story of the proximity fuse is much more than a simple narrative of technological invention. It is, in fact, a profound reflection on what it means to win a war and on the price of victory. When one thinks of weapons and conflicts, the first thought that comes to mind is often brutality, destruction, and pain. But along this journey, it becomes clear that behind the creation of the fuse is an even more complex moral issue: the use of intelligence to win, but without losing humanity. The real revolution brought about by this small device was not only military, it was in essence a victory of ethics and reason against barbarism. Merle Tuve, the physicist responsible for creating the fuse, faced a decision that many scientists who participated in the war effort also faced: how to use knowledge responsibly. He knew that his invention could save thousands of lives, but it could also be a tool of death, using science to kill, or to save lives by killing less. This moral dichotomy is the real crux of the proximity fuse story. It was not just an invention to increase mortality, but rather an attempt to make conflicts more efficient, to avoid the uncontrolled carnage that marked previous wars. Applied science was not made to glorify destruction, but to limit it while achieving victory with greater precision. American engineers, mostly young and driven by an ethical force, worked tirelessly with the awareness that their research was directly linked to human suffering, but also to the possibility of alleviating that suffering. They were not fighting for fame or recognition, but for justice, and this was reflected in the creation of the fuse, which instead of being an instrument of indiscriminate killing, became a means to avoid unnecessary deaths. The proximity fuse, by causing explosions to occur at the most effective time, represented an attempt to change the nature of warfare. Instead of bombing indiscriminately, the fuse allowed for a more calculated, more precise, more human-like attack. And this paradigm shift brings a question: can one really overcome barbarism without becoming barbaric? In a world at war, where atrocities were a constant, the creation of the proximity fuse became a symbol of resistance to blind and uncontrolled violence. The real victory lay not in the number of enemies killed, but in the ability to restrain death, making it a matter of necessity rather than desire. This became a mission that was not only technological, but deeply human. The engineers who participated in the development of this technology were not fighting for glory. Many of them were immigrants or young scientists with no experience in battles, but with a clear understanding of the impact their inventions could have. They were motivated by the need for a solution, by the urgency of saving Allied lives. But what's even more impressive is that, amidst the chaos of a devastating war, they managed to preserve their own humanity. Unlike the military, who saw war as a form of conquest and destruction, these scientists were looking for ways to end unnecessary and prolonged killing. The proximity fuse, with its internal logic and precision, reflected an attempt to end the carnage while protecting lives. Not just the lives of allies, but also the lives of civilians and soldiers on the other side, whose deaths would now be prevented by the precision of the technology. The reflection that this moment provokes in us is much deeper than just a praise for a military invention. The proximity fuse, unlike conventional weapons, which sought mass destruction, represented an attempt to rationalize warfare. He represented the ability to, even in times of extreme brutality, use knowledge responsibly. And that's what makes his story so unique. It's not just a story of military victory, but of an attempt to preserve, as much as possible, human values, even when you're at war. And as we reflect on the history of this small device, the biggest lesson we can take away is that science can and should be used to minimize human suffering, even in the most adversity moments. The irony of this story is that in a war marked by brutality, the real triumph was the use of intelligence to limit death and suffering. In the context where the goal was simply to win the war at any cost, the proximity fuse was a response that not only made the enemies lose, but in a way preserved the dignity and humanity of those who resisted. It was a victory not only over the forces of the enemy, but also over the darkest forces of human nature, the will to destroy without thought of the consequences. The impact of this invention was not only technical, but moral. It reflected the ability of scientists and engineers to maintain an ethical and responsible view of their work in the midst of the chaos of war. The greatest victory, therefore, was not the destruction of the enemy, but the preservation of humanity in the most extreme conditions. Like Maltuvi and his colleagues, many other scientists throughout history have made their choices in the name of a more humane future. And that's what makes the proximity fuse more than a simple invention. It was, in the end, a symbol of how science, when used with purpose, can be more powerful than any myth of racial purity or desire for achievement. And in the next chapter, we'll look at how this ethical victory wasn't limited to the battlefield, but helped shape the future. The story of the proximity fuse, a weapon that looked like it came out of a science fiction tale, is actually a clear symbol of Germany's ideological and military collapse. By ignoring the importance of technological innovations such as this, and underestimating the ability of a free society to mobilize its intelligence and industry on an unprecedented scale, the Germans marked their own defeat. The fuse was not just a technical solution, but a reflection of American industrial superiority, which turned the war into a conflict of algorithms, logistics, and precision, and no longer just brute force or mythology. While the Nazis continued to rely on the archaic belief in racial superiority and pure military strength, the Allies were moving forward with a quiet technological revolution. The impact of this small device, in the final analysis, was the rupture of an entire military doctrine that for decades had been considered invincible. This story leaves a profound lesson for all of us. Logistics determines strategy, and volume trumps tactics. When it comes to modern warfare, a nation's power is not just about the number of soldiers or the amount of weapons, but rather its ability to produce, adapt, and apply science and technology on a massive scale. This is what led the United States to victory, not only its industry, but its ability to transform inventions into a production system that exceeded all expectations. The real strength was not on the battlefield but on the production line, in logical reasoning, and in collaboration among people from diverse backgrounds, all united by a common goal, to win the war in a more efficient, more humane way. When a senior Nazi commander later reflected on the defeat, he would have to admit, with a hint of bitterness, that we were defeated by trucks. This perfectly encapsulates the irony of his defeat. It was not heroes' battles, but an unbeatable logistical model, with the ability to generate a massive, coordinated force that brought down the German Empire. If you were impressed by the facts we brought to light, enjoy this video and subscribe to the channel to support the research and search for historical truth. Leave a comment below saying what was the most shocking data you discovered along this journey. Don't forget to activate the bell so you don't miss the next devastating historical fact that we are going to reveal. And don't go away yet. Listen to the next true story that will appear on the screen. Always remember, logistics determines strategy. Watch the next video here on the channel with another amazing story.